Oh, 1 plus or minus. Oh. Well, I guess we'd write cosine theta minus 1, all right? Is equal to plus or minus 1 minus cosine squared theta. Is that agreeable? I subtracted 1 from both sides and added the opposite of the radical to both sides. And then if I square this and square that, then I get cosine squared theta minus 2 cosine theta plus 1 is equal to 1 minus cosine squared theta. That's going to give me 2 cosine squared theta. Oh, that's what I did wrong here. I didn't put the square here.
That's why.
Oh, I
so that
forgot all
one's
about
root
the
of
square. No
cosine.
wonder I was having trouble.
Yeah,
Okay.
isn't that cosine? That one on the left is cosine.
On the left.
Yeah,
This would be
on that
cosine
side.
squared.
Yeah, cosine squared.
Right, but I wanted sine instead.
Yeah.
Right, so, okay, so now if I add sine squared to both sides, I'll get 2 sine squared plus 2 sine theta equals 0. And divide by 2, I get sine theta times 1 plus sine theta equals 0. So either sine theta equals 0 or sine theta equals negative 1. And there they are, right? So
it's-
here
Found it.
and here.
Should work with both of them, right?
Sorry?
Should work with both.
Yeah, right, and those both turn out to be true, right? If I plug in theta equals 0, I get 1 minus 0 equals 1. If I plug in theta, or sine theta equals negative 1, and cosine is 0, 0 minus negative 1 is also 1. Right, so those are, so then what are the solutions then? Well, theta is equal to any multiple of 2 pi, or 3 pi over 2. Put a k there. Yeah. All right, well, that was a weird one, huh?
Yes.
So that, what was that? That was number 14, huh?
When this is on the exam, is there a particular notation you want us to use to show how it can repetitively have multiple answers after every 2 pi?
Yeah, that's the 2 pi k, just what I'm writing.
Just like that?
Yeah. Yeah, use the 2 pi k notation. And that's going to be important in chapter 8 as well, or wherever that is, which is the final frontier for this course. Okay, so how about number 30? Here we got tan 3 theta plus 1 equals secant 3 theta. We're just woodshedding a lot of these. So tan 3 theta plus 1 is equal to secant 3 theta. I think that's what I wrote, or what I read. Yeah. All right, so here we have a multiple angle situation, right? So, I mean, there is an identity for tan 3 theta, which you can substitute in there, but that's not the game here, right? So we want to solve for 3 theta, and then find all solutions for 3 theta, and then divide those by 3. But what? We want to get this in terms of one trig function, right? And how can we do that? Well, you can write in terms of sine and cosine, but you're going to have the same problem.
Yeah, but you can multiply by the conjugate at that point, possibly.
Yeah. So what if you were to write in terms of, say, you have sine 2 theta over cosine 2 theta? Does this help?
2 or 3.
Oh, 3. What am I writing 2? This is 1 over cosine 3 theta. Did that help? So now instead of tan and secant, I got sine and cosine. I could multiply both sides by cosine. But that's problematic, right? Because I could be multiplying by 0, in which case I'm picking up extraneous solutions. So rather than doing that, I can say, well, if these things are equal, then their squares are equal, right? So, does that help to square these things? tan squared, squared, 3 theta plus 2 tan 3 theta, oh no. Plus 1 is equal to secant squared 3 theta. Can I write this in terms of one trig function now?
Professor, question on that.
Yeah.
You know how you said when you square root something, you get kind of like you get data loss when you do that? If you were to do the same thing in the situation where you multiplied cosine 3 theta on each side, does that same thing happen?
It's not so much data loss as data creep. So you're going to get extraneous solutions, right? Wherever cosine 3 theta is 0, that's going to be a solution to the new equation. Multiplying both sides of an equation by 0 makes it true, right?
So
Where it wasn't true before.
Isn't that the same thing where you square root something and you actually get an additional value that can also hold true?
Well, square roots are typically get plus or minus, right, in general. So, yeah. But I'm saying here, if these things are equal, then they're squares. Now, they could be these things are opposites and their squares are equal, right? So when I'm done here, I need to check, did I square opposites, right? So I don't have an equivalent equation anymore. But I do have an equation which I can get in terms of 1. So remember the identity for secant squared? It's not up there. Oh yeah, it is. Secant squared is 1 plus tangent squared, right? So this is 1 plus tangent squared theta, 3 theta, right? So now I can subtract the tangent squared 3 theta from both sides. Okay, well that's good. I can subtract the 1 from both sides. Oh, that's even better. So what do I get then? 2 tan 3 theta has got to be 0. Huh. Is that true? Okay, so then tan 3 theta has got to be 0, right? And where is that true? Wherever 3 theta is a multiple of, it's pi over 2 plus a multiple of, I guess any odd multiple of pi over 2. So I can write this plus k pi. But when I write that, I should maybe get a common denominator. See what's going to happen when I get a common denominator? I'm going to get pi plus 2k pi on the top, which I prefer to think of as 2k plus 1 times pi over 2. Right, so what is that? Well, if k is an integer, then 2k is an even integer, right? If I add 1 to an even integer, I get an odd integer. So you want to think of this as an odd multiple of pi over 2, which is just where the tangent function is 0, right? So now, when I solve for theta, see now I've solved for 3 theta, I can just say, well, okay, take 1/3 of that, right? I get this. But we need to check these, right? Do these really make the original equation true, or do they make the squares equal? But so let's test. So theta could be equal to, if k is 0, that's pi over 6. If k is 1, what do we got? Pi over 2. If k is 2, we got 5 pi over 6. If k is 3, so this is k equals 0, k equals 1, k equals 2, k equals 3. We got 7 pi over 6, and what's the pattern here? Looks like I'm just adding 2, huh? Pi over 6, 3 pi over 6, 5 pi over 6, 7 pi over 6. The next one would be 9 pi over 6, which reduces to 3 pi over 2, right? So where are these places on the circle? Well, pi over 6 is here, pi over 2 is here, 5 pi over 6 is here, 7 pi over 6 is here. So I keep adding pi over 3, right? 3 pi over 2. And another one will take me to 11 pi over 6. and we need to test them, right? So what if, theta is equal to pi over 6? Does that make this equation true? Is it true that, pi over 6, right? So that's gonna give me pi over 2 plus 1. Is that equal to the secant of pi over 6? Pi over 2, sorry. 3 times pi over 6, right? It's pi over 2. What's the tangent of pi over 2? Well, that's 0, right? Is that equal to, what do you get here?
1.
Secant of pi over 2, well, that's, that's gonna be 0, huh?
No, it's not.
Oh, sorry, that's gonna be, what am I talking about? The reciprocal of cosine pi over 2. Cosine of pi over 2 is 0. Right, so, wait, oh, I see, this is not 0. This is the other 0.